You are cruising at speed when the helm begins to vibrate and the outboard engine suddenly cuts power. When you reach for the throttle, the remote control is dead and the engine refuses to enter gear. This is the dreaded Suzuki fault code 7-5. It indicates that the communication line between the console's boat control unit and the engine control module on the transom has been severed. The DF300AP utilizes a drive-by-wire system, meaning there are no physical cables linking your hand to the throttle or gear sets. The engine's movements are dictated entirely by digital signals. The system responds to the loss of signal by triggering an intentional active failsafe. It locks the controls to ensure the 300-horsepower engine cannot accelerate or shift without a stable command. A common mistake is to open the engine cowling and look for jammed physical linkages. When the digital signal dies, mechanical inspections are a waste of time. To resolve this code, you must follow a rigid diagnostic hierarchy: power, wiring, connector, resistor, and finally, the module. Technicians who jump straight to replacing the engine control module often find that the 7-5 fault remains. The module is rarely the source of the failure. Successfully clearing this code requires moving away from traditional mechanical troubleshooting in favor of a systematic network evaluation. If you are at sea when this happens, perform a hard reset. Shut off the battery switch for 10 minutes to drain the modules of residual power and clear temporary software glitches. If the code returns, focus on the two main physical failure points: the socket behind the remote control and the main harness located under the engine cowling. Look for signs of saltwater oxidation. Even a small amount of green buildup inside the connector pins creates a physical barrier that stops data transmission. With the ignition on, perform a wiggle test. By moving the harness slowly, you can force intermittent loose connections to reveal themselves on the diagnostic gauge. In a drive-by-wire system, the operation of the entire engine depends on the integrity of a single microscopic data pin. Most localized 7-5 failures in the field trace back to the sub-battery cable. This small wire runs directly to the battery and powers the entire digital network. Use a multimeter to verify the voltage. The system requires a steady supply between 12.6 and 12.8 volts to maintain communication. This graph illustrates the sensitivity of the system. If the power supply drops below 10 volts, the drive-by-wire network crashes instantly, regardless of the condition of your wiring. You must also verify the main system ground. If the ground connection is loose or corroded, the electrical current cannot exit the circuit correctly. This creates a floating ground. The current seeks an alternative path and often surges back through the thinner CAN bus data lines. Because these data wires cannot handle high current, the surge causes thermal damage that can burn out the communication chips inside the ECM. Stable power protects the data network. It serves as the primary barrier preventing the engine's control modules from being destroyed by their own electrical supply. To test the data lines, the system must be powered off. You cannot get an accurate resistance reading while the network is active. The CAN bus network uses two 120-ohm terminating resistors, placed at opposite ends of the communication line to stabilize the signal. Because these resistors are wired in parallel, a multimeter reading of exactly 60 ohms indicates the network architecture is healthy and intact. If the multimeter shows 120 ohms, one of the terminating resistors is missing or broken. Without the second resistor, data signals hit the end of the wire and reflect backward. This creates digital noise that prevents the ECM from decoding the information. A reading of OL or infinity indicates that the CAN bus wires have been severed completely. A reading of 0 ohms reveals a direct short circuit, meaning the two communication wires are physically touching each other. Mastering these ohm readings allows you to visualize the exact structural failure within the network without having to strip the entire harness. Identifying the fault is the first step, but the repair itself requires precision. Applying old-school mechanical habits to the system can cause permanent damage. Never use jumper cables to start a DF300AP. The resulting voltage spikes will instantly destroy the microprocessors in both the BCU and the ECM. Avoid forcing the gear linkage. These engines use electric actuators to shift. Attempting to move them manually will break the internal actuator gears. Do not splice broken data wires with standard connectors. Splicing changes the resistance of the line and will trigger recurring communication errors. Using aggressive mechanical techniques on a drive-by-wire system often turns a simple wiring issue into thousands of dollars in hardware replacement. To fix the 7.5 fault permanently, replace damaged harnesses rather than repairing them, apply anti-corrosion spray to every connection, and reboot the system software. You must use the Suzuki Diagnostic System tool to clear the error memory. The engine will not exit failsafe mode until the fault history has been digitally reset. Always verify the 3 pillars of the system: clean power above 12.6 volts, a secure sub-battery connection, and a 60-ohm network resistance. Modern marine technology is managed through electrical architecture. The most effective technicians measure and verify before they ever begin a repair.